macroscopic displacement efficiency. Okay. So trapping on the micro or pore scale by capillary force or field scale by aerial or vertical bypassing. Okay. When you see this figure, okay, initially your green part will be represent your oil. Okay. Green part will be represent your oil. Okay. And blue part will be your water. So in first at initial condition, so oil are in your continuous phase. Okay, in porous phase. When you apply primary recovery or secondary recovery, so there is a small amount of oil will be left here, and here oil is not in. When you see the third figure, oil will not in continuous phase, and water is in continuous phase after primary or secondary recovery. So that amount of oil will be trapped in your micro pore spaces, and to recover that oil from the micro pore spaces is and the efficiency is known as microscopic displacement efficiency. Okay. Got it? So basically microscopic displacement efficiency is that the displacement of your oil at your pore space with the displacing fluid. Okay. Displacement of your trapped oil in pore spaces or micro pore spaces with the displacing fluid is known as your microscopic displacement efficiency. Okay. And how to increase our micro displacement efficiency? What are the factors behind to increase our microscopic displacement efficiency? Or we can represent microscopic displacement efficiency will be ED. Okay. To increase microscopic displacement efficiency, first one is decrease the interfacial tension. Okay. Decrease IFT fluids. Okay. So how you increase displacement efficiency? Because these oil are trapped in the pore space, so you decrease the interfacial tension, so it improve the oil mobility. Okay. Second will be your oil volume expansion or reduction oil density. Okay. If the density of your oil will be reduced, so your trapped oil will be move easily. Okay. Other case will be to reduce oil viscosity. Okay. Or Other case will be reduce capillary pressure. Okay. So to increase our displacement efficiency, microscopic displacement efficiency, we have to decrease interfacial tension between the fluid and decrease the oil density or reduce the oil viscosity and reduce the capillary pressure. Okay. So we can improve our microscopic displacement efficiency. Got it? Microscopic displacement efficiency. Have you any doubt in this? So if the question is asked how to increase the displacement efficiency and four option are given here this and other option will be given all of the above. So answer will be the all of the above. Okay. And mathematically you calculate the displacement efficiency using this formula. Okay. SOI your initial oil saturation. Okay. SOR is your residual oil saturation. SW is your SWI initial water saturation. Okay. And SW is the water saturation at your SOR. Okay. So if the data is given and to calculate the displacement efficiency, so you can directly use this formula SOI minus SOR upon SOI. Okay. If SOR is SOI or so SOI is equal to 1 minus SWI. Okay. SOR is equal to 1 minus SW. Got it? No, no, sorry. Oh, okay. So now calculate the displacement efficiency. So this in that formula question will be asking GATE 2017 Okay, relatively permeability curve are shown in the following figure, and a water oil system in porous medium. SW is the water saturation at, and Kr is the relative permeability. Curve 1 is the permeability of water, and curve 2 is the relative permeability of oil. Assuming the porous medium is an irreducible water saturation initially, the maximum possible recovery of oil by water flooding is. So, so you have to calculate ED, displacement efficiency, using that permeability curve. Okay. So we have the formula SOI minus SOR divided by SOI. Okay. Or other formula 1 minus SWI. Okay. So there are two formulas. Okay. So first you can apply both, either first or second, your answer will be same. Okay. So from the permeability data, first you note down the values of SOI and SOR. Okay. So how to read permeability curve? The saturation will be increasing on x-axis and the permeability will be increasing at y-axis. Okay. And your curve 1 will represent your permeability of water and curve 2 will be represent your permeability of oil. Okay. So your permeability curve of water will be start from 0.25. Okay. So the initial water saturation SWI is equal to 0.25. Okay. And at that point, you calculate your residual oil saturation. Okay. Because your permeability curve will be touched here. Permeability curve of oil will be touched here. Okay. So initial oil saturation will be, as the saturation of water increases, your permeability, your saturation of oil will be decreases. Okay. You get you got that point? Saturation, when you are start producing your well, saturation of water increases and saturation of oil will be decreases. Okay. So what is the value of initial oil saturation? So you can calculate directly 1 minus SWI. So you calculate the value of, okay. So SOI will be 1 minus SWI. So 1 minus 0.25 is equal to 0.75 your SWI. Okay. Got it? Now you calculate SOR, residual oil saturation. So SOR will be equal to 1 minus SW. Okay. So at the end of your water curve, water permeability curve, which is shown in curve, which is shown by curve 1. Okay, so SW at that point will be 0.8. Okay, so 1 minus 0.8, the value will be 0.2. So SOI and SO are calculated. Now you calculate the ED. So ED will be SOI means 0.75 minus 0.2 divided by 0.75. So your answer will be 73.33%. Okay, you got it? You got it that point? How to calculate the relative permeability? How to calculate the saturation values from the relative permeability curve? Okay. Have you any doubt in this? Okay. So this is the case of your microscopic displacement. Okay. So now we see the macroscopic displacement. Okay. So macroscopic displacement will be your calculated from the material balance. Okay. Or macroscopic displacement will be caused by aerial or vertical bypassing of the oil. Okay. When you see this figure by example of aerial bypassing, and at that corner you start injection, and first figure you start injection. Okay. So you start water to sweep your oil volume. Okay. So due to heterogeneity present in the reservoir, okay, so your water will be bypass the oil and cannot sweep efficiently your oil. Okay. As the flood continues, the water swept zone grows, but the difference in mobility of oil and water and heterogeneity in the reservoir cause fingering. Okay. So this case is the fingering, viscous fingering. So what happens in viscous fingering? When you push the low density fluid or low viscosity fluid, oh sorry, when you push the, if this is your reservoir, okay, and in that your oil will be filled. So oil will be higher viscous than your water. Okay. So when you, this is your production well. Okay. And this is your injection well. So in injection well, you inject water. So what happens? Your water viscosity will be less than your oil viscosity. You know that or not? Because oil will be more viscous than water. Okay. Got it? So in your reservoir, your oil will be filled and the oil dense viscosity will be higher. Okay. So when you inject water from the injection well, so what happens? Water having low viscosity. Okay. So what happens? It creates a channel due to heterogeneity present in the reservoir. So that phenomena is known as viscous fingering because your injected fluid having low viscosity than your reservoir fluid. So viscous fingering occurs. Got it? So this is the case of aerial sweeping until a continuous path of water develops. Then only water can be produced. Oil in the unswept zone cannot be recovered by the continued water injection. Okay. Once your water will reach your production well, so only water will be produced, so no oil will be produced in that case. Okay. And this is the example of vertical bypassing. Okay. So here you inject your injection fluid into your injection well. Okay. As water is injected, it displays the oil towards the production well. Okay. As the flood continues, the swept zone grows but different in gravity and reservoir heterogeneity cause fingering and override. Okay. So once your water reach to your production well, so only water will be produced in that case. Okay. So macroscopic displacement efficiency. Macroscopic displacement efficiency or volumetric sweep efficiency. Okay. So to calculate the macroscopic displacement efficiency and volumetric sweep efficiency, so there is a formula EV. EV represented by your volumetric sweep efficiency and EI represents your vertical sweep efficiency and EA represents your aerial sweep efficiency. Okay. Because volumetric sweep efficiency are the phenomena are causing by both aerial or vertical bypassing of the injected fluid. Okay, got it? Or you can calculate EV using that formula NP by VP SOI divided by BOI minus SOR divided by BOR. Okay, NP is your produced oil displaced. Okay, VP is your pore volume, reservoir pore volume. SOI your initial saturation, BOI your initial formation volume factor. Okay, SOR your residual oil saturation after your recovery, and BOR is your residual oil formation volume factor. Okay, so you can calculate these two formula. If your vertical sweep efficiency and aerial sweep efficiency is given, so you can multiply it directly and to calculate volumetric sweep efficiency. Okay, if the data is given, so you can calculate if the SOI and BOI and SOR, BOR, NP and VP is given, so you can calculate EV using that formula. Okay, got it? So a question is come in to get 2016. So in that question, in an oil reservoir flooded with water, the volumetric efficiency EV is given 0.70, 70%, and the connate water saturation as WI. Connate water saturation means initial water saturation is given as WC or as WI. Okay, is your zero point 0.4, and the residual oil saturation SOR is given your 0.3. Now calculate the overall efficiency. Overall efficiency will be denoted by recovery factor RF, and it is the multiplication of microscopic displacement efficiency and volumetric sweep efficiency. Okay, so to calculate the total overall efficiency of the reservoir, first you calculate ED using this formula. Okay, and the formula of ED will be SOI minus SOR divided by SOI. Okay, got it? We discussed that formula in previous concept. Okay, so here SWC is given initial or connate water saturation. First you calculate SOI. So SOI mean equal to 1 minus SWC. Okay, so zero point 0.4 is given, 1 minus 0.4, your 0.6 will be SOI, and ED will be your 0.6 minus 0.3 divided by 0.6. Your 0.5 ED will be your calculating 0.5. So your overall efficiency of the reservoir will be ED calculated 0.5 and EV is given 0.7. So what the value of total efficient recovery will be 0.35. Okay, or 35, because per question will be asking in percentage. So it will be 35%. Got it? Have you any doubt in this? Have you read that before in your college? Enhanced oil recovery, that topic? So now next concept will be your mobility ratio. Okay. Mobility ratio. Because volumetric or aerial sweep efficiency and vertical sweep efficiency are strongly influenced by your mobility of water. Okay. So we have to consider mobility ratio. Okay. So mobility will be represented by lambda. Okay. Lambda d will be mobility of displacing fluid, and lambda small d will be mobility of displaced fluid. Okay. So mobility ratio is that which is denoted by M, capital M, and it is the ratio of displacing fluid to the displaced fluid. Okay. Mobility of the displacing fluid to the displaced fluid. Got it? So if M is greater than 1, what happens? And if M is less than 1, what happens? Okay. If M is greater than 1, it means your displaced fluid will be lower than displacing fluid. Okay. So it is your unfavorable condition. Okay. If M is less than 1, it is your favorable condition because your displacing fluid will be more displaced. Okay. Or oil will be produced more. Okay. Displacing fluid in that case, if this is your reservoir, okay, and you inject water here, and your oil will be there. Okay. So which one is your displacing fluid and which one is your displaced fluid? Okay. So in that case, displacing fluid here will be water. Okay. And your displaced fluid will be oil. If the mobility of displaced fluid will be greater than your mobility of water, so your ratio will be less than 1 and the oil will move easily than water. Okay, got it? Or if mob represents MOW represents that water flooding process mobility ratio, and it will be represent that KRW by KRO and mu divided by mu mu W. Or you can write that KRW by mu W divided by KRO divided by mu. Okay. Relative permeability of oil or water, relative permeability KRW, relative permeability of water, KRO, relative permeability of oil. Or you can, we know that relative permeability is the ratio of absolute permeability and your effective permeability. So this equation will convert Kw mu W and Kw of relative permeability of oil to convert into permeability, effective permeability, and mu of viscosity. Okay, got it? So you can calculate relative permeability or mobility ratio using that equation. Okay. So one question will be asked in GATE 2016, I think. Where is the question? Hmm. Sir, we can write SOR, yes, 1 minus SW. Yeah, this is the question. You see question number 4. A heavy oil reservoir is flooded with a line drive, assume one-dimensional flooding. Okay. The fractional flow of water, FW. Okay, let me tell you FW, fractional flow. Okay. Okay. After fractional flow, we discuss this. Okay. Okay. So in our reservoir, there is a heterogeneity present. Okay. So aerial heterogeneity and vertical heterogeneity. Okay. So to represent the vertical heterogeneity, there are three methods. Okay. So to calculate the vertical heterogeneity, there are three methods. First one is permeability variation factor. Okay. Second one is Lorentz coefficient. Lorentz coefficient method. Third one is cross flow index method. Okay. So first method is permeability variation method, or we can say that or DeCosta-Parkinson method. DeCosta-Parkinson method. Okay. So what happens in that method? So we calculate the permeability variation coefficient in DeCosta Parkinson method. Okay. And assumption of this model is reservoir is represented by non-communicating layer. Okay. So if this is your reservoir and this will not communicate to each other. Okay. Non-communicating reservoir and gravity segregation is neglected. There are two assumptions to assume that. Okay. And there is a formula which is given by this method, DeCosta and Parson. These are the two scientists. Name of these two scientists and the method name is also on the name of that scientist. Okay. So there is a formula is given V K minus K sigma divided by K. Okay. So permeability at 50% water saturation or at 50, and minus K sigma means your permeability at your 84.1 and divide by K50. Okay. So there is a chart which is given. Okay. And there is a portion number of sample 1, 2, 3 and up to 100. So there are 100 samples. Okay. And on y-axis sample permeability. Okay. K. And the permeability will be given in millidarcy. Okay. So there is a data of 100 data. Okay. Sample 1 having other data and sample 2 having other viscosity and sample 3 having other permeability and sample 4 having other. So using this method, we take the permeability of 15th sample, 50th sample. Okay. So this will be your, we can say that this is your 50 and this is your 84.1. Okay. So these taking the permeability of that sample, the sample permeability of 50th sample. So to draw a line from 50th sample. Okay. On that slope and read this value of permeability. Okay. And then you draw the line from 84.1 on that line and corresponding that draw perpendicular. So you read that value. So this is the value of K84 0.1, and this is the value of K 50, or K average, K bar, and this is the value of K sigma. Okay. So directly you can calculate the permeability variation coefficient. Okay. So when the value of V is 0, so this represents your perfectly perfectly homogeneous. Okay. When the value of V is equal to 1, it is highly heterogeneous. Okay. And the value is equal to 0.7. So assume that no data available. Okay. Got it? So in Parson method, there are two assumptions. What are these assumptions? First one is no no communicating layer will be present. Okay. Second one, segregation drive is neglected, or gravity segregation is neglected. Okay. So these two scientists give that formula K average, K bar minus K sigma upon K. K bar means the permeability of 50th sample, and the K 84.1 the permeability of 84.1 sample. Okay. And to calculate the V, permeability variation coefficient. Okay. If the value of permeability variation coefficient is 0, so the our reservoir formation will be perfectly homogeneous formation. If the value of V is equal to 1, it is highly heterogeneous. If the value of V is 0.7, we assume that no data available. Okay, got it? Or you can calculate V using these curves. Okay, because permeability variation coefficient versus mobility ratio. Okay, so using these curves between permeability variation curve and your mobility ratio curve to calculate the recovery factor. Okay. So, and with respect to W, or water oil ratio. So for water oil ratio will be 1, 25, 50, 100. 1, 5, 25, and 100. Okay. Only four curves are there. Okay. So you calculate V from K50 minus K84.1 divided by K50 using that formula. Okay. And we have the mobility ratio formula KRW by KRO mu by mu W. Okay. So to calculate permeability variation coefficient and mobility ratio. Okay. So according to the question, if they are asking regarding 0.25 WOR ratio, so our equation will be this. R is equal to 1 minus 0.32 SW. Okay. So let's see that question. Okay. Consider permeability variation V is 0.3 and saturation will be 0.30. Okay. And mobility ratio is 0.25, 0.26. So in which the primary recovery was 10%. Okay. So first we calculate the recovery for one water oil ratio is 1, 5, 25 and 100. Then you compare that. Okay. Got it? So if that value of V is 0.3, let's see this curve. You have the value of V is 0.3 and M is 2.6. So this is your semi-log scale. Okay. M in on log scale and permeability variation on your linear scale. So you draw the line from the your permeability, which is given here because permeability variation coefficient is 0.3 and M is 2.6. So this one is 2. So this one is your 3. So 2.6 will be in between that. Okay. So draw a line from here and draw a perpendicular line from that. Okay. So that point will be your, so there the equation is given here. So R is equal to 1 minus SW and this value is your that point at where your mobility ratio point and permeability variation coefficient line intersect each other. Okay. So we say that this point will be 0.21 or 0.22. Okay. So SW is given 0.3. So we can calculate R. So R is your recovery factor 1 minus 0.3. So 0.21. So you can calculate this. Similarly, for that curve. Okay. Your M is 0.3 or 2.6 and your permeability variation coefficient will be 0.3. So you draw a line. Okay. Your this one is your 2. This one is your 3. So 2.6 will be in between that. Okay. So 3 will be here and this will be your 2.6. So in that case, your equation will be R1 minus 0.72 SW. Okay. Equal to, and this point will be your 0.32. Okay. So you calculate your recovery factor using that curve. Okay. Got it? But on that concept, no question will be asked in previous year. Only permeability variation coefficient will be question on permeability variation coefficient will be asking. Okay. So you have to memorize that formula. Got it? So that question is also from previous gate questions also. Okay. All those questions are discussed in today class are from previous gate questions. Okay. This is the list of previous gate year questions. Okay. If you have any doubt in any other previous gate question, you can ask me. Okay. And all this sheet I send you. Okay. You have to solve that question yourself. Okay. And if you have any doubt, you can ask. Okay. So this is the first method to calculate the vertical permeability, okay, or vertical sweep efficiency. So second method will be Lorentz coefficient, which is represented by L. Okay. So there are two scientists, Shalmaz and Remy, which gave that concept in 1950. Okay. So they are only considered single parameter that describe the degree of heterogeneity of the phase zone. Okay. So only Lorentz coefficient is based on plot permeability thickness product and porosity thickness will be represented by H. Porosity thickness product. Okay. So to calculate the data of permeability and permeability thickness product and against the porosity thickness product. Okay. And you calculate the Lorentz coefficient. Okay. So Lorentz coefficient will be represent only two values. Either L is equal to 0, either L is equal to 1. Okay. So if L is equal to 0, so your formation will be completely homogeneous. And if L is equal to 1, so your formation will be your completely heterogeneous. Okay. And third method will be your calculating cross flow index. So cross flow index will also give the data between if these are these reservoirs. Okay. If there is a reservoir and these are the layers, if cross flow index gives that either your adjacent layer are communicating to each other or not. Okay, so cross flow index only given that. Okay, and the value is cross flow vary from 0 to 1. Okay, if cross flow index is 0, so the layer between the adjacent layer are not communicating. Okay, on non-communicating layers. And if cross flow index is equal to 1, so it means that your layers will be communicating. Okay, so your layers will be communicating. Got it? So these are the three methods to calculate your, which gives that your reservoir will be homogeneous or heterogeneous. Okay. First method is your permeability variation coefficient. Second method is Lorentz coefficient. Third method is your cross flow index. Okay. These are the three methods. Okay. Have you any doubt in that? Or we can go to next topic. So our next topic is fractional flow equation. Okay. So during the life of a water flood, so there is a pattern of injection and production well, and there is a spacing between them. So the objective of our water flood project is to maximize our oil recovery. Okay. So the development of plan hinges on the expected increase in recovery, whether the incremental oil justifies that capital expenditure and operating cost. Okay. So FW represents that your fractional flow of water. Okay. So FW is equal to QW by QT. QW is flow rate of water and QT is your total flow rate. Total flow rate will be your flow rate of oil plus flow rate of water. Okay. Or this is your water cut equation, or we can say this is your water cut equation also. Okay. FW is your water cut. How much water cut are present? So you can calculate using this equation. FW is upon FW is equal to QW upon QT. QT will be your total flow rate, either over water or your oil. Okay. So to convert these flow rate into this equation at your reservoir condition. Okay. So to convert this equation at your surface condition, so FW is your at reservoir condition. Okay. And FW is at your surface condition. So all the values of flow rate will be in your surface condition. Okay. So there is a relationship between reservoir FW and surface FW. Okay. So how can you calculate that? Because QWS is equal to where surface flow rate QWS is equal to Q naught by BO. Okay. Or QWS means water at surface concentration. So QW by BO and QOS is equal to QO upon BO. Okay. So put these two values in this equation. So QWS will be your QW slash BW divided by QW slash BW plus QO BO. Okay. If the form if you have the data at reservoir condition, so you can calculate FW at surface condition. Okay, using this formula. Okay, but your FW has a relationship between water oil ratio. Okay, so what is the water oil ratio? WOR is your flow rate of water divided by flow rate of oil. But FW, wait, so WOR is equal to water oil ratio will be represented by QW by QO. Okay. QW by QT or QW divided by QO plus QT or QO. Okay. So now you take the common QO from first equation, this equation. Okay. So FW will be, you take the common or you divide the Q naught on LHS on numerator and denominator. Okay. So this will convert into WR because according to the definition, WR will be the flow rate of water divided by flow rate of oil. So FW is converted into WOR at reservoir condition, because these values are at reservoir condition. Okay, plus 1. Okay, about that, and you can calculate WOR from here. FW1 minus FW. Simply arrange the equation. Okay, and there is a relationship between reservoir FW and surface WORS. Okay, so surface water oil ratio will be QWS divided by QOS. Okay, got it? So FW is equal to QW plus Q. So we know that QWS is equal to QW by BW, and QOS is equal to QO divided by BO. So from that equation, QW is equal to QOS. Sorry. So QW is equal to QWS into BW, and your Q small QO is equal to your QOS BO. So now put these values here. Okay. So QW will be QWS BW. Okay. So your QWS BW plus QOS BO. Okay. So now you divide QOS on numerator and denominator. So QWS BW divided by QOS, and QWS BW QOS plus BO. Okay. So now this will convert into your WOR surface, because WOR surface is equal to QWS divided by QOS. So WOR surface into BW divided by BOR surface BW plus BO. Okay. So this will equal to FW at reservoir condition. You got that? Okay. And there is a relationship WOR surrounding is equal to BOFW divided by BW 1 minus FW equal to WOR at reservoir condition BO divided by BW. So these are the fractional flow equations, and you can interchange any of the equation, okay, from surface to reservoir condition. Okay, you got that equations? You have to memorize that equation. Okay, so fractional how to derive we know that FW is equal to QW by QT. But now you convert the fractional flow equation into convert in terms of mobility ratio. Okay. So we know that the Darcy law. Okay. So all the flow Q or QW will be given by Darcy law. Okay. And we know that the pressure gradient PC is equal to capillary pressure is equal to pressure of wetting non-wetting phase minus pressure of wetting phase or pressure of oil minus pressure of water. Okay. And the fractional flow rate of oil FW is equal to 1 minus FO fractional of oil. Okay. Or FO is equal to 1 minus FW because total cut will be 100%. Okay. So now you consider the steady state equation to and these two fluids are immiscible to each other and consider homogeneous system. Okay. So to apply the Darcy law minus first for apply the oil phase and consider the gravity effect also. Sin alpha. Alpha is the deep angle. If the well are in horizontal, so the alpha value will be 0. So sin 0 will be 0. These term will be 0 in horizontal flow. Okay. Similarly, you can write the equation for QW for water flow equation. Okay. So this equation is your 1. This equation is your 2. So we know that the capillary equation PC is equal to PO minus PW. Okay. So del PCX by del PC by del X. So del P naught by del X minus del PC PW by del X. So first minus second. What you get or second minus first because minus sign is there. Okay. If minus sign goes inside, so this will convert into minus and this will convert into also minus. If minus sign goes inside, this one will also minus and minus. So 2 minus 1. Okay. And the equation will convert into and take these values here. Okay. QW mu down A minus Q naught mu naught upon K naught A and del P naught by del X minus del PW by del X minus G W minus rho of oil sine alpha. Okay. So in place of this bracket, you can write this PC to convert this PC. Okay. So del PC upon del X minus G del. Okay. And this equation is same here. Okay. So we know that FW is equal to QW by QT. Okay. So QW is equal to FW QT. So to convert these QO and QO value, QW and QO value in terms of FW. Okay. So QW is equal to FW, and similarly Q naught is equal to 1 minus FW naught QT. Okay. And substitute these values in place of QW and QO. So your equation will be FW QT mu W divided by KW A minus 1 minus FW QT mu divided by KO A equal to del PC divided by del X minus G rho W minus rho naught sin alpha. Okay, we got it up to this. Now using variable separation method, so your equation will be converted into this. Okay. Okay. So now neglect the capillary force as in comparison to viscous force. Okay. And your alpha angle will be 0. So this term will be 0. So in comparison to capillary effect is small. So this term will also 0. And FW is only there. So what will be left? FW is equal to, all in upside will be cancelled out because capillary pressure is small in comparison of viscous force. Small in compared to viscous force. Okay. So F and your alpha angle will be 0 in case of horizontal flow. Okay. So your FW equation will be 1 upon 1 plus KO divided by KW mu W divided by mu naught. Okay. And we know that the mobility ratio. What is the value? What is mobility ratio? KW by KO into mu O by mu W. Okay. So FW will be 1 upon 1 plus 1 by M. Okay. You got it? So this one is also one relationship. This is also other relationship, and FW is equal to QW by QT, or QW is equal QT is equal to Q naught plus QW. So all these equations are used for to calculate the fractional flow. Okay, and in term this equation in terms of your effective permeability, and if this effective permeability is not given and relative permeability is given, KO is converted into KRO and KW is converted into KRW, and mu W and mu will be same. Okay. Now solve this question, and this question will be last for today. Okay. So solve the question number 4. Okay. So we know that the formula of fractional flow. Okay. FW is equal to 1 upon 1 plus KR W divided by KRO divided by KRW, and mu W divided by mu O. Okay. So in question number 4, what is given? A heavy oil reservoir is being flooded with the line drive, and the fractional flow of water is found to be. So FW is given. What is the value of FW? 0.75 barrel by barrel. Okay. At water saturation of 60%. HW is 60%. Okay. A polymer solution with twice the viscosity of water is used and displacing the phase. Okay. So in first case, you inject directly flooded by water, and then you replace the water with polymer. Okay. So what happens? So first you calculate the mobility ratio of water oil case. Okay. So this term will be your M. Okay. So fractional flow of water oil case when your water oil system, which is given by 0.75. Okay. So 0.75 is equal to 1 upon 1 plus 1 by M. Okay. We know that this is our mobility ratio. Mobility ratio of first mobility of water with oil. Okay. Got it? So now you calculate M from here. So 1 plus 1 by M WO is equal to 1 by 0.75. So your point is 3, 4, 4 upon 3, and 1 by MO is MWO is equal to 4 upon 3 minus 1. So it will be 1 by 3. Okay. And your MWO mobility of water oil ratio will be 3. Okay. So now read the second case. A polymer solution with twice the viscosity of water. A polymer solution, viscosity of polymer will be the twice the viscosity of water. Okay. Using the displacing, used as a displacing phase. And the permeability curve for the water flooding and polymer flooding are same. So the permeability of KRW will be equal to the permeability of polymer. Okay. So write the formula of permeability of polymer oil system. So you only replace the permeability of water with the permeability of polymer. KRO divided by KRP into mu W will be replaced by mu P and mu O will be same. Okay. So we know that the permeability of water will be, relative permeability of water will be equal to relative permeability of polymer. So KRO divided by KRW. Okay. But the viscosity of polymer is twice the viscosity of water. 2 into mu W divided by mu O. So 2 is common, take as common. KRO divided by KRW into mu W divided by mu O. This is the mobility ratio of polymer and oil. Okay. So this value is equal to your M, normal M of water and oil. Okay. You get that point? One by M. Okay. Because the fractional flow equation is equal to FW is equal to 1 upon 1 plus 1 by m. So this value is equal to 1 by m. So this value is equal to 1 by m. Sorry. We write wrong equation. Mobility of polymer oil will be Krp divided by Kro and mu divided by mu p. Okay. So your relative permeability of polymer is equal to the relative permeability of water, and your oil viscosity and oil permeability will be same, and your oil viscosity of polymer will be twice the viscosity of your water. Okay. So you take 1 by 2, and this will convert into your M, mobility of water and oil. And we have calculate water and oil mobility will be 3. So polymer MPO will be 3 by 2. Okay. So now calculate the fractional flow of polymer water solution. So now put the value of MPO here. So 1 upon 1 plus 1 by 3 by 2. So your fractional flow equation answer will be here equal to 0.6. Have you understand this question or not? I can explain again if you say, or if you're not understanding that concept. Okay. Pawan and Tej, have you any doubt in this question? Okay, please explain one more. Okay, no problem. So now first you read that question. A heavy oil reservoir is being flooded with a line drive, assume one-dimensional flooding. Okay. The fractional flow of water is found to be 0.75 at water saturation 60%. Okay. So initially you flooded with water. Okay. This is your reservoir, and this one is your production well. So your oil will be producing in upward direction. Okay. And this one is your injection well. Okay. So at initial state, your fractional flow in that case, when you flood it with the water using water, FW is equal to 0.75. Okay. So no other value are given. We know that FW is equal to 1 upon 1 plus 1 by M. Okay. And mobility, and this mobility is equal to the, because this system is only water flood, so the mobility is only between the water and oil, because water is displacing your oil in that case when you inject water. Okay. So FW value is given, so you calculate MWO from this equation. Okay. And this will comes 3. What he is saying, a polymer solution with twice viscosity of water. Okay, a polymer mu viscosity of polymer is twice than viscosity of water, and relative permeability will be K RW is equal to KRP. Okay. So he says that when you replace water with polymer. You inject polymer here. So now FW will be changed because your mobility ratio will be changed because it replaced by water to polymer. Okay. So now you calculate the mobility ratio of polymer and oil. Then you calculate the fractional flow of in that case. Okay. So now we know that the mobility ratio formula, normal mobility ratio formula, KRW divided by KRO, mu divided by mu W. Okay. So now this formula is in terms of water oil mobility ratio. And then you write the polymer oil mobility ratio. So you replace the water subscript with polymer KRP, KRO, mu O and mu P. So now he say that so this value you calculate and the value is 3. Okay. Now you calculate the value of this one. Okay. So other data is not given, only these two conditions are given. So you replace the polymer viscosity with water viscosity because there is a relation, and polymer relative permeability to water relative permeability. Okay. So water relative permeability is equal to the KRP. Your KRO is same, mu is same, but you write the viscosity of polymer, it is the twice of viscosity of water. So you take common MPO equal to 1 by 2 KRW is equal to KRO mu divided by mu W. So it will be equal to this mobility ratio of oil and water. Okay. You got that point? So to replace this value with MOW, so MPO is equal to MPMWO minus divided by 2. So this one is 3. So this one is 3 by 2. So now you got this. You put the value of MPO in this equation. You calculate the fractional flow value. Okay. You got that point? Hello,
Yes, sir.
Pawan. Have you understand
Yes.
this?
Yes, sir.
Okay. So you have to practice that question at your own. Okay, and if you have any doubt at that time, you can ask again. Okay, because questions on in that topic is very important from the gate point of view. Okay.
Okay, sir.
Okay. So these all these questions that we have discussed in today's class are coming in previous gate question. Okay. So you have to solve that question. Okay. And I'll send the module by today or tomorrow. Okay. You have to practice that question. Okay. So one topic is your syllabus. Concept of pattern flooding is covered. Recovery efficiency is covered. Permeability heterogeneity is covered. Macroscopic and microscopic displacement efficiency is covered. Only one concept is left of to calculate the fractional flow is Buckley-Leverett frontal advanced theory. So this theory will be discussed in our next class. Okay, and we start the EOR methods in next class. So how your interfacial tension and your oil mobility ratio will affect on your recovery in chemical flooding, polymer flooding, and what are the mechanism of polymer flooding and miscible flooding. Okay. Okay. So now you may leave, or you have any question, you can ask.
Sir, your which topic is important, sir?
Sorry.
Sir, in your which part the questions will come, sir? Numerical questions.
So numerical part. Okay. So
Yeah, sir.
numerical question. So according we have to analysis that, and all the question will be asking numerical question asking from the efficiency part. Okay. Recovery efficiency part. This question is also from your recovery efficiency part. Okay. Question number 1, 2 is your basic concept. This concept will be left, and question number 3, and it will be discussed in tomorrow class. Okay. And you see this fractional flow equation in question number 4. Relative permeability curve will be asking. Okay. So basically most of the question are asking from today class in EOR. Okay. 95% question will be asking on today's class concept. Okay.
Okay, sir.
So this question is also from your displacing and displaced phase or mobility ratio on mobility ratio. Okay. All the question are asking mobility ratio and your Buckley-Leverett theory and efficiency. Okay. So today's class is important from the question for the question. Okay. And remaining concept will be discussed tomorrow. Okay. Have you any doubt?
Also,
So Pawan, have you take previous classes also, or you
sir,
seen the
yes,
recorded
sir.
lecture?
I have seen recording lectures, sir.
Okay. If you have any doubt on that recording lectures, you can ask me. Okay. We will
Okay, sir.
discuss in additional class. Okay. We will take an
Okay,
additional class for doubt session. Okay. If you have any doubt, you can ask me there.
okay, sir.
Okay. Okay. Good evening. You may leave.